Hi everyone, welcome back. So in this video, we're going to talk about derived rows and columns. So this is a very important topic for the Adam principles. So this is the part 8, number 8, understanding when to create derived rows versus derived columns and analysis model dataset for clinical trials. Okay, myself, Ali Sheikh, I'm the consultant at Tile Optima Inc. Okay, let's continue with this. So the introduction part, so the training focus mostly on Atom implementation guide version 1.1, and if you go to the 4.2 sections, the creation of the derived columns and version versus creation of derived rows, and the reference material will be Atom model version 2.1 and Atom implementation guide version 1.1 and acronyms reference documents. This training module will equip clinical data scientists with knowledge to properly determine when to derive rows versus columns in Atom dataset following the CDISC standards. Okay, the table of contents overview, introduction to derived rows and columns in Adam datasets, building the BDS domain, process of constructing the basic data structure domains and rules for derivations. So there are 6 essential rules governing when to create new variables versus new records. Okay. Okay, so what is the overview? So understanding when to create derived rows versus derived columns is a fundamental to proper Adam dataset constructions. So this determines how your analysis data will be structured, impacting both analysis efficiency and regulatory companies. So usually the biostatistics or clinicians, they will request you to do this to create the new parameters as per the SAP, or you are creating the new derived columns. So what are the rules as per the CDISC Adam implementation guidelines? So what are the main rules we have to follow before you create these rows and versus derived columns? Okay. So let's example the BDS data structure origin. So the basic data structure datasets typically derive from single SDTM finding domains. So the ADLB from laboratory LB, VS, vital signs, and EG for electrocardiogram EG. So the basic BDS domain, no additional parameters or imputed records needed. So simple one-to-one transformation from SDTM. So when you have a complex BDS domains, additional parameters, imputed records required. Okay, if you follow the specific rules in Adam IG 1.1 section 4.2. So what is the difference? If it is a basic ones, you don't need any parameters, additional parameters to create or any imputed records just for transform to HDTF. So when you come to the complex BDS domain, so there will be have some additional imputed records or additional parameters you have to be created. Okay, so building the BDS domain, the process of converting raw clinical data into analyzable datasets require careful consideration of the structure and derivation of methods. So building a proper BDS domain requires understanding both SDTM and the source data structures and the analytical needs of statisticians and clinical reviewers. Okay. Okay, so the building the BDS domains, identify the source data. So determine which SDTM domains will contribute to the BDS data. So typically single findings domains and add analysis variables, create aval C and other analysis ready variables based on SDTM values. And the map core variables, transfer the required variables from SDTM to Adam, so including the sequence variable and the test code and category variables. And you have to apply the derivation rules. So follow the rules from section 4.2 from of Adam IG to determine when to create derived rows or versus the columns. Okay, so here, so next one would be so to building the BDS domain, they should be have a key components. So you'll be having the identifier variables as study ID, unique subject ID, and the timing variable, analysis visit, study date, relative study date, and time point. And the parameter variables, you will be having param code, analysis variable, aval, character value of aval, base, and change, etc. And the supplementary qualifiers relevant to analysis needs. So these are the main key variables be present in the BDS domain. Okay, so here are the rules. The rule number one, the basically new variables. Is we are going to create the new variable, and the new rule two would be the new parameter based on the existing single parameters. So you have to create the new parameter based on the existing single parameter. And the rule number three, adding a time point. Okay, and the rule number four, the new parameter based on multiple rows from a single parameters. Okay, so if you have a multiple rows, maybe you can take average of the multiple rows to create a new parameter from the single parameter. And the rule number 5, new parameter based on the two parameters. If you have multiple, like for example systolic blood pressure or diastolic blood pressure, so you can take the consideration of these two parameters and creating the new parameters. And the rule number 6, the new rows due to multiple baselines. So as I mentioned, there will be some subjects have the multiple baseline values, so you have creating the new rows based on the multiple baselines. Okay, so the rule number 1, when creating an analysis variable that applies to all existing parameters, add a new column rather than new rows. Okay, this is rule number 1. And the new parameter from the single parameter. So when creating a new parameter based on the single existing parameter, add new rows with a distinct param code. Okay, so it will be having a distinct different param code. And rule number 3, adding a time point. When adding an analytical time point not present in the source data, create new rows with appropriate timing variables. Okay. Okay, so the next, the new parameters. The parameter configuration is a critical component of a system architecture that impacts performance, security, and functionality. When introducing the new parameters, developers must follow the structure rules to ensure the system integrity. So these rules establish a standardized approach to parameter management across the distributed systems, helping to maintain the consistency and prevent conflicts during implementation. Okay. so so what does it mean? So because if you are using the new parameters, they should have follow some critical components of like impact, performance, security, and functionality. Make sure it meets the new parameters as per the param must follow this, like the structure rules to ensure the system integrity. You should have to follow the standardized approach to creating the new parameter. Okay. So here are the new variables. So the new variables should be the definition. What is the new variable? The new variable represent a distinct data point that hasn't previously existed in the system. It requires careful implementation to ensure proper integration. So new variable should only be added. It is derived from the eval or for parameter. No further analysis need to be done. So implementation requirements, so unique identifiers across the system namespace, clear data type specification, and default value declaration, access control permissions. And the documentation standard, all new variables must be documented with users examples, constraints, and depending relationships to the existing parameters. So these are some important requirements, implementation requirements if you need to create a new variable. Okay, so the rule number 1 is the technical specification. Okay, so the rule number 2, the new parameter based on existing single parameters. Okay, so the lab unit is reporting requirements when creating the new parameters from existing SDTM variables for dual unit reporting. SI and conventional unit strict traceability must be maintained. The key SDTM variable that must remain unaltered when included in ADAM datasets. Okay, so the whatever the SDTM variables are present, it should not be changed. So when you're including in the ADAM datasets. So rule number 3 is adding the time point. Okay, so when and how. So rule 3 is to address how properly add a new time points to existing parameters in analysis dataset while maintaining the data integrity and traceable to the source data. Okay, this approach allows for derived analysis time points that were not collected directly in the original SDTM datasets but are required for statistical analysis. So basically, when inputting the missing data or creating the derived time point, so it creates a new record, new derived record within the same parameters, and it only retains SGTM and ADAM variables values on the new row. That makes sense. Okay, so here, so it's create a new time point basically that has the average result of all the post baseline observations. And adding a time point implementation. So the original time point, so preserve all original SDTM time points with their corresponding numeric format of the visit and the TPT values. New time point creation, add derived time points using appropriate new visit, and values. Then sequence values, the sequence to missing for derived time points to indicate they were not, so they were not in the source. So then we have the documentation, document the derivation method analysis, so dataset specifications. When adding the time points not present in the original data, you must maintain a clear distinction between the observed and the derived values, so ensuring the analysis results remain traceable to source data. So make sure it should have some differences between the original, the observed values as well as to derived values. to make it more traceable in the source data. Okay, so next, fourth one is rule number 4, rows from multiple rows of a single parameters. So when you're creating a new parameter derived from multiple observations of the same parameter, you must follow specific implementation guidelines to maintain the data integrity. Common example, creating average values across multiple time points or deriving a maximum value for a series of measurements. So here we'll be having multiple rows and you're creating one single parameter. So the example will be the average values when you have multiple time points. Okay. Um, so the implementation details, the function of the multiple rows within the parameter should be added as a new parameter, especially when creating the derived values based on multiple observations. To create a new parameter, define a new parameter when deriving the values from multiple observations of the same test. Example, mean of multiple post baseline values or maximum or minimum values across the visits. Handle time points appropriately. Assign appropriate visit values that represent the derived nature. So analysis visit might be average of post baseline, and analysis visit numeric may be special value, like you can say 999. So the consider baseline handling determined if a baseline and change from the baseline calculations are needed may require additional derived parameters or document derivations logic is clearly. So that is the rule number 4. So these are some proper implementations how we have to handle if we have multiple rows to create a new parameter as a single parameter. So the rule number 5, the function of the multiple parameters. So when creating a new parameter that combines the data for multiple different parameters, special consideration must be applied to ensure the proper analysis data set structures and traceability. So this rule addresses scenarios where biochemical and clinical relationship between the different measurements need to be analyzed together. So the implementation principles identify the source parameter. So basically determine which original parameters will contribute to the derived value. Example, you will be having the HDL for cholesterol ratio calculations, then match corresponding time points, ensure the measurements used in calculations come from the same time points, maintain the consistent visit structure between the source and derived parameters, and apply calculation algorithm. Implement the mathematical function that combines the parameters, document the exact formula used for derivation, and assign the new parameter metadata. Create appropriate param code numeric form of parameters. Set appropriate categorization variable, category of param 1, 2, etc. So these are some implementation principles how we have to handle the rule number 5 if you need to create the new parameter based on the multiple parameters. So rule number 4, example, total cholesterol HDL ratio. So the source parameters are two distinct laboratory parameters. Total cholesterol, so total cholesterol will be param code CHOL and param CD HDL. So these two are two different parameters. So each parameter has a measurement across multiple visits from screening through week 12. So we have for the derivations 245 divided by 47. So it gives 5.21. That is will be the new parameter value for that one as an example. So here the implementation results new derived parameter so maintains the identical visit structure while implementing the calculation algorithm. So the new parameter definition, the total cholesterol HDL ratio, the param code is CHLH and the paramen 77, the new unique numeric identifier. And the visit structure preservation will be having analysis visit will be maintain the same identical visits and will be preserving the same numeric of the visit, and the LV sequence to be missing derived value because this is the derived values. And the calculation implementation, so you'll be having the formula here by giving the screenings all time points calculated consistently. So this approach enables statistical analysis of the cholesterol ratio while maintaining the clear traceability to the source parameter. So here we will the Adam analysis model provides standardized just overview of the Adam dataset rules. So standardized structure for clinical trial analysis datasets that are clear, traceable, and reproducible. Okay, so the analysis dataset should have the clear documentation, enables clear understanding of the analysis data creation methods. So it should be traceable, direct path between SDTM source and data and analysis results, and the most important, reproducible, facilitate recreation of analysis results and derived variables. Okay, so we'll be focused on rule 5 and 6, which handle functions of multiple parameters and multiple baseline definitions. So the rule number 5, as we continue the function of the multiple parameters. When implementing the functions of multiple parameters in Adam dataset, each derived parameter must follow the specific requirement. So assign analysis baseline flag for baseline identification, typically week 0, and calculate the base value where analysis baseline value flag equal to y, and derive the change variables change percentage change for all records, and assign the sequential values within the domain. Okay, so the example shows the three parameters: the total cholesterol, HDL, and derived parameters. So here, to identify the baseline record, ABLFL equal to y for week 0 record for each parameter. And the step 2, the populate the baseline values. Copy eval to base where analysis baseline value equal to y, and propagate all records for each parameter. Okay, so and the next step 3, the calculate the change variable. Change, you calculate the eval minus base, change cross base into 100. And step 4, assign the sequence variable. So these are the implementation how we have to do when we are deriving the new parameter based on the existing three parameters. Okay, existing two parameters or multiple parameters. So next, rule number 6, multiple baseline definitions. So here when a study requires more than one baseline definition, so each definition is to own set of records with distinct calculations. For example, a study might need separate baseline for different trial phases run in double blind and open label periods. So as I mentioned, you can see in the image, you will be for each clinical trial will be having multiple phases as it screening phase and double blinded and open label phase. Okay, so they should be like each phase will be having multiple different baselines. So create a base type variable, classify records by baseline type, run in dbl ol. So which baseline is indicating for this? So we have the values running are either double blind or open label. Then we'll be having generating records copies and duplicate relevant records for each base type which appropriate classification, and identify the baseline record. Set ABLFL equal to y for the appropriate record within each param code or base type combination, and calculate baseline dependent variables. Calculate base range indicator, shift 1, and other derived variables within the base type group. Okay, so we'll be having multiple baseline examples. So after processing for each baseline type, records marked with analysis baseline flag equal to y base value populated. Okay, so here range show the baseline normal range indicator. So here you can see, so they have three different phases. Epoch represent the elements of the phases. So you'll be having running, double blind, and open label, and eval values are different for each phase. And range of indicator have the indicator will be the different. So normal, low, high, I can see. So what is the shift show changes from baseline to normal range? Okay, so we have to check multiple. So start a comprehensive example, putting it all together, starting SDTM data. For example, height, weight parameters with measurement across the multiple study phase. So running, so we measure all running treatment available. So we measure all of them in height, weight parameters, all these three phases. So the required derivations, create last observation carry forward record for missing time points, then derive weight 2 parameters, weight cross 4, derive WH parameter, weight cross slash height, calculate the average by epoch, implement the three types of. So this is example of how the required derivation for creating the new record. Okay, by epoch, by new baseline record. So the creating the LOCF record when implementing last observation carry forward, we identify missing record, find the time points with no observations in the datasets. So create derived records, create new records with the d type equal to LOCF at missing time points, and propagate values. Yes, to identify the missing records, find time points with no observations in the dataset, and create derived records. So they create new records with the d type equal to LOCF at missing time points. So for the variable of the d type, so you'll be having the name called as LOCF for the creating the new records. Wherever you see the records are derived, that d type variable will be LOCF at the missing time points, and the propagate the values, copy eval analysis range, lower value, higher value, range indicators from the most recent observations, and update the metadata. So set analysis with the numeric and epoch to reflect the new time point. Okay, So the deriving the new parameters, deriving the W2 parameters of weight cross 4, duplicate all weight records, change param CD to W2, multiply aval by 4, and adjust the reference ranges, analysis range lower and higher values, and preserve all the other variables. So the next is the following the similar approach to the weight cross height average calculation by epoch. Multiple baseline implementations derive variables base change, percentage change, and shift one. So each step builds on the previous transformation to create a complete analysis ready Adam datasets. Okay, so the creating the weight and height derived variable. So this example demonstrates the creation of the weight slash height ratio with predefined normal range parameters. The source data structures height and weight measurements are collected across the multiple visits and epoch. So we'll be having run-in treatment and open label with the reference ranges, analysis range lower and higher determining the normality status. So the calculation method, weight ratio with the height after calculation assign the fixed reference ranges. So 3 and 4 and the normal range classification the based on the calculated value and reference ranges and also determined if it is less than 3 it we have range of indicator will be low, and if it is between 3 and 4 is normal and greater than or equal to 4, then it will be considered as a high. So you can see the graphs is here. So if it is a 4 we consider as a high, that is in the running, and the normal high and the normal will be in the treatment and open label. Okay, so this is the creating the WH derived variables. Okay, so the next one would be if you so the calculating the averages by parameter and epoch calculation process. Average records are derived for each parameter by epoch, including the last observation carry forward records. The calculation follow these rules. So the group data by param code and epoch, calculate the mean eval within each group, and assign the special indicators analysis visit 11 and the TRT for TRT for the blinded phase, and the analysis visit 77 for open label. So set visit num vs sequence to missing values. Okay, so here add d type equal to average to identify the derived records. The d type will be average. That is the method we have using for the inputted new parameters. So derive analysis range indicators based on the calculated oval and reference ranges. Okay. So the adding the baseline types by epoch. So run in baselines. First record run in epoch per param code. So use it as a reference for all records. Analysis baseline flag equal to y for this record. And the treatment baseline first record in treatment epoch per param code. Use it as a reference for TRT and open label epochs. ABLFL y equal to y for this record. And open label baseline. So first record in open label epoch per param code. Use it as a reference for open label epoch only. Okay, so and this one also equal analysis baseline flag equal to y for this record. So each record in the dataset is assigned as a base type, and baseline flag is marked for the first record of each parameter within the respective epoch. Okay, so this structure enables multiple reference points of analysis. Okay, so if you go to the next slide, so there are some baseline implementation for height parameters. So the key implementation details for each height record base type is assigned based on the epoch designations. So the all record receives run-in base type designation for primary analysis. So record in treatment epoch also receive the treatment base type for treatment specific analysis, and open label epoch also receive the base type for open label analysis. For each base type, exactly one record per parameter is flagged as a analysis baseline flag equal to y. Because so the next one, the baseline implementation for the weight parameters. So the baseline types, each parameter receives 3 baseline designations to enable multiple analysis perspectives. So one record per parameter one record by base type combination designated as a reference point baseline flag. And the baseline structure enables calculation of the change, percentage change, and shift analysis. So the weight square parameters baseline implementation follow the same pattern as other vital parameters. The record from each epoch receive the corresponding base type designation with one record per parameter flagged as the reference point for each baseline type. So the basically what they're saying that if there is a multiple phases for a particular subject for a particular parameter, so each will be having the analysis baseline flag equal to y, um, for the baseline value, and there will be having some the baseline base value and baseline flag, and also will be having the change and percentage respect to the particular phase. Okay. So the derived parameter considerations for weight and height ratio, baseline records are identified independently as source parameters. So analysis baseline flag equal to y is assigned for the first record within each epoch. So each epoch like run-in and blinded and open label. So all records receive run-in baseline designations. So treatment records receive both run-in and treatment designations, and open label will be receiving the running treatment open label designation. This approach ensures consistent analytical capability across all parameters, regardless of whether they are directly measured or derived. So here the derived parameters require the same baseline structure as the primary parameters to enable consistent analysis. Okay. So the creating the derived analysis variables, the baseline value. So value the parameter at baseline determined by base type. Each record inherits the corresponding baseline value based on it in its base type. So the baseline reference indicators, normal range indicator at baseline can be low, normal, or high. So change from baselines, absolute difference between aval and minus base, quantify absolute magnitude of the change, and the percentage change relative difference aval minus base slash base standardized change relative to the baseline, and the shift from baseline, so category shift in reference range normal to high. So these derived variables enables comprehensive analysis of the changes from baseline, facilitating the statistical assessment of treatment effects and clinical significance. So you'll be having the base and baseline range indicator change and the percentage change shift one. So these are the if you want to create the analysis baseline variables, so you should have all these variables. Okay, so the change analysis logic, analysis variable for the weight parameters. So the base value at baseline recording according to the base type, and the change aval minus base absolute change, and the relative change percentage change, and the shift one text representation or reference range change. Baseline records have change percentage value of 0 as they are compared to themselves. So in when you have baseline flag equal to y, so these two variables will be the values will be the 0. Okay. So the key principles of derived variables in clinical data. So consistent calculation methods. All derived variables must follow the standardized calculation rules to ensure consistency across analysis. Document all derivations algorithms clearly, and the multiple baseline references. Maintaining the multiple baseline types, run-in, treatment, open label, enables the flexible analytical approaches at sensitivity analysis across different trial phases. Okay, so the change variables, both absolute and relative change variables, provide complementary information about the treatment effects and should be interpreted together. So the implemented these derived variables techniques in your clinical dataset analysis workflow to enhance interpretations of the treatment effects and safety signals. Okay, the statistical consideration, always verify derived variables through QC process. So document LOCF, other imputation methods. Consider sensitivity analysis with the different baseline definitions and flag shifts between reference ranges for clinical review. Okay, so these are some important considerations if you go through step by understanding these principles when you're creating the new parameter based on the baseline, when you're creating the baseline based on the phase of different phases. Okay. All right. So these 6 rules are very important to make it in your understanding of ADAM implementation guideline before you do new derivations of any new parameters or new row, creating the new rows or columns. When we're doing this, they should have to follow these principles. Okay, that's it for this video. Thank you so much for listening.